Hello and welcome to my talk today about improving the developer experience of infrastructure as code and GitOps using the Cubestack framework. So the agenda for the talk, first I'll talk a little bit about what is this developer experience gap that I see, and we'll discuss how frameworks solve this developer experience gap already on the application development side. I'll then give a quick demo so you can see the Cubestack framework in action and see how Cubestack brings the same developer experience from application development to infrastructure as code. And then we will start the main part of the talk where we will look at the code of the framework, features and the reusable components it provides, and we discuss how things are implemented and why they are implemented this way. Before we go there, I want to give you a little bit of background on myself. I started my career in IT when I dropped out of law school and started the cloud control path in 2009. And so for the last 10 years, I've done a lot of public cloud and containers. For the last 5 years, I've done a lot of Kubernetes as well. I think it's very clear that if you look at the developments in the cloud native community, that a lot of effort went into improving the developer experience of every aspect of building, testing, deploying applications on top of Kubernetes. Meanwhile, however, I think the developer experience of infrastructure as code lags very far behind. I think this is a problem for two reasons. The number one is if there is such a high barrier to entry, a lot of teams are prevented from benefiting from infrastructure as code, and obviously the benefits are real. And the other aspect is I don't really see what's the point about all those advanced deployment automation if the cluster it sits on is managed manually via UI and is thereby the weakest link. So to get this started, let me explain what I mean when I say developer experience gap in the context of Terraform and Kubernetes. I think overall I see three main issues. First one is the upfront effort. So if you are new, there's a very steep learning curve to both Terraform and Kubernetes, of course. But even if you're not new, you constantly reinvent the wheel every time you start a new project. For example, having to figure out the repository layout, set up remote state, configure service accounts in IAM, write a pipeline, set up triggers for CI/CD, all these kind of things. And it doesn't stop there. So you also have a lot of long-term maintenance effort. A production-grade Kubernetes infrastructure as code base can easily become thousands lines of code, right? This covers the Terraform configuration, but also Kubernetes YAML, your CI/CD pipeline file. And all of this is not a static code base. Kubernetes is moving fast, so you may remember 1.16 API version of network policies and deployments and stateful sets and a number of others had to be updated. And there's a similar change upcoming for Ingress with 1.22, if I remember correctly. Also, the cloud providers are moving very fast, sometimes have to deprecate features or services, which trigger you to make changes to your code base. And Terraform itself is also evolving. So both 0.12 and 0.13 have added long-awaited and very useful features, but they both also came with the migration effort. And then finally, there's the slow feedback loop when working with infrastructure as code as a team, because the remote state forces you to always fall back to committing, pushing, and running Terraform through the CI/CD pipeline. If you don't, you risk the code base and the state being out of sync when multiple users try to do this, and you will definitely see weird Terraform plans as a result of this that can be quite confusing. And so if you look at these problems, they're not unique necessarily to infrastructure as code. They exist also for application development languages, but there we have a solution for these in the sense of these use case specific frameworks. Right? So if you need a full stack framework, web application framework, you would probably go with something like Django if you're a Python shop, or Rails if you're a Ruby shop. If you're building a cloud native application in Java, using Spring Boot will get you there much faster. Or if you're building one of those new Jamstack websites, using a framework like Gatsby also has tremendous value. And so these frameworks, by being use case specific, they reduce the upfront effort simply by providing reusable components for all those common requirements this use case has. And they also reduce the maintenance effort because it's shared with the community. Yes, under the hood, they have a lot of moving parts, but if you're a user of the framework, you can just follow the updated versions of the framework. You don't have to care about the underlying individual components. And then finally, because they're so use case specific, these frameworks can also provide a much faster feedback loop. Usually they do this by providing these auto-updating local development environments, where you automatically rebuild whatever application or website it is as you make changes to the code base. And so on the infrastructure as code side, using Terraform to automate Kubernetes, in my opinion, is a very similar, very specific, and very popular use case. So the idea behind Cubestack is, if we're building a framework that's use case specific for this infrastructure as code use case, we can still provide the same benefits in developer experience as the frameworks on the application development side do. Of course, this begs the question, why did people not do this earlier? And I think the reason here is that it didn't really make sense to have a framework like this before the paradigm shift to containers and Kubernetes, simply because the stack was very different and you didn't have those common requirements. So if you look at operating systems, they're a fairly weak abstraction layer, but they're also traditionally owned by ops teams or infrastructure teams. But because the applications leaked requirements in forms of dependencies or maybe configuration into the operating system, the teams that manage the platform layer would oftentimes have to build the automation specific for that application. And this left very little room to have these common requirements where a framework with reusable components could offer value. Now this changed with containers and Kubernetes for two reasons. First, we have another instance of the operating system inside the container. And this one is the one which we configure application specific, right, with the dependencies and the configuration. And this can also now be part of the responsibility of the application team. And additionally, we have the Kubernetes API. The Kubernetes API with its declarative building blocks that describe what an application needs to be kept running, further built this very powerful abstraction at the boundary between platform layer and application layer. And this means now the platform layer is much more easily kept entirely free from application-specific requirements. And this means now there are common requirements for a platform layer, and a framework with reusable components can provide value. Additionally, I think if you look at where the cloud native community is heading, this abstraction of the platform layer is only getting stronger, and this will further increase the value infrastructure as code frameworks can provide on the platform layer. Now, before we jump into learning more about how the Cubestack framework implements these features, let's start with a quick demo of how this looks like. I have an empty directory currently. The first thing the framework offers is a way to scaffold a new repository. Do this with the Cubestack repo init command, and then you would select a starter. I'm going to do GKE here for this example. So if I execute this, I now get this new directory, and this includes everything I need, both provision the Kubernetes infrastructure as well as configure those Kubernetes clusters in terms of namespaces, RBAC, but also cluster services that I need on the cluster before I can deploy application work. All of this is integrated into this one repository. And you would also have, for example, the Docker file that helps you run this both for bootstrapping locally, also for emergency recovery if the automation isn't working, but also is used to provide a unified environment every time the CI/CD pipeline runs. So first thing you do is when you're in the repository and you want to work on a change, you start the local development environment, which you do with Cubestack local apply. And while this is coming up, I'm going to explain real quick how this works. So if you take a look at the clusters TF file, you see that we load Cubestack's module for a Google cluster. And for all these cloud providers, Cubestack maintains a set of modules, always the real cloud cluster module and a cluster local variant. Both accept the same input variables. But when the local development environment starts, it reads your Terraform configuration and detects one of these cloud modules, and then it replaces transparently the source here with the cluster local variant, and instead of talking to the cloud provider, it will provision Docker containers locally that simulate these clusters and their nodes. This is done using kind, Kubernetes and Docker via a Terraform provider for kind. And then the other thing you see in here is the configuration file. We'll talk a little bit more about this later, but here is where you have configuration for each one of the clusters you specify and their respective apps, ops, and log environments. So you can see at the bottom that this local development environment is now up and running. And what we can do now is that it's watching for changes. So when we start working on either RBAC or namespaces, or we would install cluster service like Prometheus operator so that we can add monitoring to our cluster capabilities, or we change cluster nodes, or we add additional clusters to the clusters TF, because we could also have more GKE clusters in here, or we could have them in the same region or different regions, or we could also add multi-cloud clusters in here. Can simulate a lot of these requirements in the local development environment and drastically shorten the feedback loop we have. And then once we're happy with our changes locally, we can commit them to a branch and push the branch to start the review process with our team. Now that we've had a sneak peek at Cubestack in action, I want to talk about a number of the common requirements Cubestack solves, how these are implemented, and why they are implemented this way. The first one is the ability to have multiple environments. Teams need multiple environments to be able to work on and test their infrastructure automation before they promote it to a mission-critical environment. Otherwise, you're constantly performing open heart surgery on a mission-critical environment, which is not a good idea. Terraform has a feature called workspaces, and these workspaces, they're very useful to implement these separate environments. Basically, you can think of every workspace as its own individual Terraform state. This way you can apply a code base against one workspace and then change the workspace to apply the exact same configuration against the second workspace. Right? This is how you can first validate your changes in a test environment before you promote them to the mission critical one without making code changes in between. To do this, however, you have to write your modules and Terraform configuration in a specific way. So I have a simplified example here, which tries to create two GKE clusters. And the first one simply uses a variable .name for the cluster name. And the second one concatenates this variable with the variable that Terraform provides for the current workspace name. Now, what would happen if I apply this to a test workspace is that both of those clusters would get created. And if I try to now promote this exact same code also to my mission critical environment, I change the workspace, I run Terraform apply. The second example here would work because it provides a unique name for the cluster, but the first one would fail because the cluster name is already taken. So this is an example of what you need to do in your Terraform code base to work reliable with these workspaces. Cubestack takes this concept a step further, and it uses a dedicated module called the metadata module. The metadata module, based on the name prefix and the base domain that you provide as part of your configuration, and additionally provider name and the provider region that you selected for your infrastructure, generates names that are not only unique across environments, but are also unique for multiple clusters in the same environment. And these clusters can be in the same region or different cloud provider regions, and they can even be in different cloud providers. On top of the name, it also provides a little bit more, like a few other metadata entries, like a fully qualified domain name, provides the workspace, and some other metadata, and it provides these as both tags and labels. And then the framework will automatically use that metadata whenever it creates Kubernetes resources or cloud resources where labels or tags are applicable. Another example of a common requirement for infrastructure as code is the ability to have configuration that's different per environment. And so again, we're going to look at a simple example first. So a naive approach to implement this could be you can have a hash map of hash maps, like you see on top here in your config auto tf vars file, for example. and you use the workspace name as the key of the outer hash map. In this case, we have workspace 1 and workspace 2 as the examples. And then when you try to access these attributes in, for example, a module like the example module you see here on the bottom in your Terraform files, you can use the terraform.workspace variable to select the correct key from the outer hash map and then address attribute 1 and attribute 2. However, there are two problems with this approach. The first one is that as you do this, you duplicate all your settings in all your environments. Of course, it's only two, in the example, we only have two attributes, but a real configuration would have significantly more, of course. And then as you do add or remove attributes, you always have to remember to do this in all the environments. And this gets error prone very quickly, in my experience. And the other thing is that you also have to keep those values in sync. And you need to know that some values should be the same between environments and other values should be different between environments. And then this may also change during the lifetime of the code base. And as you and your team make these changes over time, it gets harder and harder to keep this correct. Also for this, Cubestack has another module that it includes, which is called the inheritance module. And this module solves this problem using inheritance, very similar to how applications frameworks oftentimes do this. So by default, Cubestack has these two environments called apps and ops. And the apps environment is the mission critical one, where your applications run. And the ops environment only exists to validate changes before they are promoted to the apps environment. Now, to prevent configuration drift between those two environments, ops inherits everything from apps, and then you have the ability to explicitly override certain values in ops that you want to have different from apps. This does not per se prevent configuration drift entirely. You can override. There is still configuration drift, but it makes any different explicit, and it makes it much easier to make sure if you make changes to something that's only configured in apps, you can rely on the inheritance to make sure this also inherits to all the other environments. We have an example here that in the ops environment overrides cluster max node count and cluster node locations on top of the settings it inherits from the apps environment. And it does so because the ops environment doesn't run any workloads, and it makes no sense to have the ops environment be the exact same scaling number of nodes as the apps environment here, which autoscales between 3 and 30 nodes, for example. So instead what we do is we reduce node locations and we reduce max node count. And the ops environment would have a cluster that's still multi-availability zone and that has multiple nodes, 2 in this case, but it doesn't autoscale and it doesn't need 10 empty nodes or something like this. So you can keep the cost down, but still keep the benefit of having an environment that you can validate your configuration against, and that you can trust to be similar enough so that a configuration you validated against ops doesn't suddenly fail when you apply it against apps. Now that we had a look at how the Cubestack framework implements environments and how it does inheritance for the configuration of those environments, the next step is to take a look at how the Cubestack framework provides GitOps workflow for teams. As I said already, Cubestack framework has two default environments called apps and ops. And the diagram you see here shows an example of how you go through this workflow. The workflow always has 4 steps. First, you make a change, then the change gets reviewed, then the change gets validated, and if everything is fine, the change can be promoted. And so the way this will work is in the middle in your Git repository, you say you branch off of a current commit, and you start working on your changes, most likely by working in this local development environment that we saw in the demo earlier. Once you are happy with your change, you would commit this to your branch, push your branch, and ask your coworkers for a review. And if there's any feedback for your review, you can just follow up with additional commits. Every commit automatically triggers a Terraform plan of the changes that you're proposing against the ops environment. So the benefit of this here is that you and your team can reason about the proposed change. And as feedback for the review, you have both the changes to the code as well as the Terraform plan output. It tells you what changes it would make to the ops environment if you were to merge this change into the main branch right now. If at some point you and your team are happy with the changes, you would merge the pull request, and this would trigger a Terraform apply against the ops environment to validate that those changes actually work against a real-world cloud environment. Additionally, after the Terraform apply, the pipeline will change into the apps workspace and then run a Terraform plan against the apps environment to give you a preview of what changes it will make to the apps environment if you now promote this change, right? So you've just validated against the ops environment, and the plan will help you understand what changes it would also do against the apps environment, which should hopefully mirror the same kind of changes that were just done against the ops environment. If you are happy with this, you go ahead and you tag this specific commit that you've just validated with a tag that triggers the pipeline again. This time it would trigger the pipeline to apply the changes against the apps environment. Right? And so now you have a workflow where you can independently, every engineer in the local development environment is free to work on their changes. At some point, they share those changes with the team, and they can run through a peer review to make sure everybody is on board with the changes, and there was nothing was forgotten, and this is actually what's supposed to be happening. You can agree on how, code quality and all these kind of things, and eventually, after a few iterations, everybody will be happy, and you can merge and validate this. And then there is the ability to control exactly which change now gets promoted also into the mission critical apps environment. As I mentioned already, these are the default environments you have, ops and apps, and ops being the one that only exists to validate and is most likely scaled down, and the apps environment being the one that runs all your applications and all your application environments. If you have the requirement to have those environments called differently, maybe you like them to be called test and prod, for example, then you can do this. This is something that you can control through configuration. By default, they're called apps and ops because I'm trying to make clear that these should be separate environments. They are infrastructure environments, right? They don't necessarily have to overlap with the environments you have for your applications. If you have this kind of a pipeline and you run it through CI/CD, then there are two things that I think are crucially important. First, the pipeline needs, like the pipeline runtime, it needs to be fast and it also needs to be resilient. There's a couple of things I do inside the framework to improve this. So on the one hand, there is a set of Docker images that I built specific for each framework release, and those will bundle the cloud provider CLIs, a Terraform version, and a number of other things. And to make sure that you have the most efficient image possible, I make very heavy use of multi-stage builds to give you a low number of layers for the final images, and also I provide variants of those images. So there's the multi-cloud variant, which would include the CLIs for all three cloud providers and everything else that they depend on. And then there's an AKS, an EKS, and a GKE specific version. And there's also the kind specific version that's used for the local development environment that we saw earlier. It keeps the pipeline runtime low by only downloading what it really needs every time within these Docker images. The Docker images are smaller if they are AKS only versus multi-cloud, for example. You may remember also from the demo that there's a Docker file in your repository, and the Docker file by default has just this one single from line, and then the pipeline starts off by building this local Docker file every time. It doesn't specify the upstream Cubestack framework image from Docker Hub directly, but instead it just inherits from it in its own Docker file. And the benefit of this is it allows you to extend the Docker file with certain requirements that you may have on top of the Kubernetes framework, so that you can install additionally CLIs or maybe, I don't know, self-signed certificates. There's sometimes use cases like this, right? So you get the benefits of a shared and maintained upstream image, but you can add additional requirements on top. Another thing the images do is that they vendor the Terraform provider. So this was a feature Terraform added recently. And the idea here is that you already have to download the Docker image and its layers. By bundling those Go binaries, which is basically what the Terraform providers are, inside the Docker image, means you don't have to additionally now reach out to HashiCorp registry and start downloading those Go binaries during the Terraform init that's going to be part of the pipeline run. This has two benefits. First is, of course, it further decreases the runtime it takes for this pipeline run to run, but it also improves the resiliency by making sure you don't additionally depend on, during your runtime, you don't also depend on the Terraform registry being up and running. The idea here is the only thing you depend on is the container registry during your CI/CD pipeline run. There's one exception, however. The Terraform modules for the Cubestack framework, as you may remember from the source we saw earlier, are specified with a GitHub URL. And so they are currently being downloaded from GitHub every time the pipeline runs. The reason for this is that I haven't found a really good way, similar to how the new vendoring for providers works, to bundle this inside the image. And also because I think it makes it very intuitive for users to understand that if they want to try something different and maybe contribute back to the framework, they can simply fork the repository in GitHub, specify their fork as the source, work on their changes, and eventually, hopefully, also send a pull request to contribute this change back into upstream, and then can also switch their repository back to using the next upstream release that hopefully then includes your changes. Let's take a moment and talk about scope. So Cubestack distinguishes between committed, desired, and current state. Cubestack's responsibility in this is to provide a workflow for teams to reason about proposed changes to the committed state and to validate or apply that to one of the environments so that you can have the validation and promotion workflow that we discussed earlier. But its responsibility is entirely syncing committed and desired state. Once the desired state has been given to either the cloud provider for cloud resources, it's the responsibility of the cloud provider to keep desired and current state in sync, make sure the nodes are configured correctly and form the cluster and that the Kubernetes control plane and the API are running. Or in case of Kubernetes resources, Cubestack will sync the committed state into the desired state inside the Kubernetes API, and it's now the responsibility of the Kubernetes control plane and controllers to ensure that Kubernetes resources desired and current state are in sync. So it's important to understand here that Terraform is not running in some sort of continuous control loop or anything, and it doesn't have to because it's triggered by changes to Git, and then syncs committed and desired state. As one edge case, imagine somebody manually through CLI or UI changes resources inside the cloud provider, changes the desired state of the cloud provider, or does the same for the desired state of Kubernetes resources. Cubestack doesn't currently solve that edge case, but the idea how to do this is basically to run a Terraform plan periodically to detect such a change, for example, every 5 minutes, and then make it configurable to either notify the team that there is such a change between committed and desired state, or to retag the last committed state to force override the desired state. This would be an area where, if somebody's interested, could get involved and contribute. Questions would be, should this run in CI/CD? Should this run as some sort of cron job or long-running process inside Kubernetes clusters themselves? I think that's a rather interesting question. Last but not least, let's talk about cluster services. So if you remember from the demo we saw earlier, there's a manifest folder in your repository. The manifest folder allows you to include any Kubernetes YAML into Terraform's plan apply lifecycle. This is useful for two main reasons. Updates to certain cluster services like Ingress or Service Mesh are difficult to test on the same cluster as the workloads that rely on them. By including these in Cubestack's GitOps workflow, these updates, like Service Mesh or Ingress, are validated in the ops environment, just like infrastructure changes, before they are promoted to the apps environment as well. And so the second benefit is that if you run a multi-cluster or even multi-cloud setup, including these cluster services in the infrastructure repository, allows you to unify the environments across clusters or even cloud providers so that your applications always find the exact same application runtime environment. To summarize, Cubestack is a use case specific framework for Terraform. It brings the awesome developer experience of frameworks from application development to infrastructure as code. And it provides everything teams need to build rock-solid Kubernetes automation. Thank you so much for your attention today. I'd also like to thank all the users who already tried the framework and gave feedback, and an especially big thank you to all the current contributors. To try the framework yourself, go to cubestack.com, click on Get Started, and follow the tutorial. You can also find the code on GitHub. It's github.com/kbst/terraform-cubestack. And if you want to support our mission to improve the developer experience of infrastructure as code, please leave us a star on our repository. Finally, the Cubestack channel on the Kubernetes Slack is the best way to join the conversation with the rest of the community. Thank you very much.